So, thank you again, Song, and the team to invite me again for doing this talk. Started a few years ago while I was at Berkeley and now moved to Oak Ridge. And we like working with you guys, and we are still trying to push this agenda of AI and computer networks forward. So this is a great opportunity to give updates and then also learn from you guys on things that you guys are working on. So we have a few updates on the AI side from our side. So we've actually started to merge the AI techniques with segment routing to actually build a truly self-driving network. So this was work that was just presented just before at supercomputing in November last year, where we've been able to work with the Polka team, which is based in University of Brazil. So we did the AI algorithms, they did the segment routing, and the team kind of came together to actually show this working in practical, which has never been done before. So we were pretty proud of this result, and we're continuing to work with them on this. So the outline of this talk is we'll introduce a challenge that why we came together to solve this, in essence, to actually build a truly self-driving network, because a lot of the discussions are still in ideas, but we want to have a practical solution. So this is where I think collaboration is key. We had a Hecate tool which does AI. So I have a picture of the overall how Hecate works. It reads in network topology and the current network real-time statistics, and it uses graph neural networks and deep learning methods to actually build graph representations of what the prediction are going to look like. And then it basically just uses a greedy approach to find optimum routing decisions, which can then be pushed down to the network. So Hecate does the AI part only. And we saw this talk done by the Polka team at SC23, where they showed a P4 setup, and they were actively able to change flow directions going from one source to the same destination, but they were able to assign it different paths in real time using free router demonstrations. So we saw them do this demo, and we were like, okay, what if we merge forces and we used our AI to the free router demonstration that you have, so that we can actually do more informed path decisions. So that's how this team came together. We actually have never worked before, but we saw each other's work, and then we were like, let's work together. So this talk is actually divided into two phases. I talk about the segment routing piece, and then I also talk about the machine learning and the results, and then the future work, which we're looking into. So this is the challenge I've been working on for a few years now. You might have seen this slide before. So how do we run networks hotter? We see in science wide area networks that there is an exponential increase in data across science. We are currently upgrading our network, which is a good solution, but we also want to see if traffic engineering can also be used to optimize our network in such a way that we can have very good performance on the network with minimum loss. We can cater to the different kinds of sciences. Like there are some sciences that are time sensitive. Some are like you can just send the data over without any deadline. So those are not time sensitive flows. Then there are latency sensitive flows, for example, clouds, control APIs. A lot of the reinforcement learning or future labs that are being designed will have latency sensitive flows, because you're actually sending actions back through AI, and you don't want to miss those. And they have to be right when you get the action, you have to do the action. Then at ESNet, I used to work before, so we have this advanced reservation system called Oscars that was able to reserve bandwidth, so you could actually do a lot of the science transfers during the time the bandwidth has been reserved. And you might have some ESNet folks in the audience over there as well. So our objective over here is that all this is great. Network engineers are very good people, and they've designed for the future. But what if we want to use our network much more efficiently, satisfying flow needs as well? So this became a combinatory optimization problem, which is defined as you want to optimize bandwidth, capacity, latency, delay, and maybe something else as well, depending on the kind of flows you are dealing with. So we have what we call elephant flows, and then we also have mice flows, but then we can also have other kinds of flows, and you might want to optimize the network for all of them together. So I started investigating this with the min-max problem, which is a very traditional maths problem which we work with. So it's basically is to do flow management for an optimum traffic engineering, such as maximum available bandwidth is used. There is unreserved bandwidth available to use, and traffic engineering metrics for special flows are done. So the min-max problem is basically you allocate flows to maximize the flows while minimizing the congestion in the network. So it is actually a purely maths problem. You can work this out. So I have a 3-node network over here on the left, where the source and the destination are shown. And then we might have another link in the middle where you are going through I to reach. And then we can define the bandwidth and latency per link. And then you also have capacity, which is represented by C. So you have two flows that are going either from SID or SD. And that you can define as the problem is the demand volume, which becomes SD plus SID is equal to H. And then you start building up the objective functions that you are trying to optimize. So for example, right here, I'm trying to minimize the flows, minimize the capacity, the bandwidth, and keeping the flows maximum. So I'm working out what an optimization function is. And then you can also add more variables to this. So maybe you want to optimize or minimize delay, and then you also want to optimize link utilization. So you keep adding to this, and this becomes a linear programming problem where you keep adding more and more constraints, which becomes more and more complex. I actually got this from the network engineering book written by Deep Mehdi. So he actually works this out in one of his chapters. So I basically just understood this whole thing from his book. Now, this can be done and solved using linear programming methods, such as if you have access to MATLAB or something to find what the optimum function for your network should be. But this optimization function is what we are making the machine learning learn for us so that we don't have to work all of these complex equations over here. So using machine learning to learn this optimal objective function. So there are many, many different constraints you can bring in. We are trying to do this self-learned. So we are using this reinforcement learning technique where you try, you learn, then you try again, something else, and then you learn again. This is a very good approach. We found some network engineering constraints that we witnessed. So from an AI modeler point of view, if you're doing everything in simulation, you have infinite amount of resources, storage, etc. So you can keep trying out different techniques. But when we try to bring this into network engineering, you have different constraints that come in. So there are flow tables that are limited by size and details of specific flows. So currently, flow tables are only designed by source, destination, and action to do. But we're thinking about different kinds of flows, right? So different kinds of flows could be could be between the same source and the destination. So you cannot have two actions defined for two different flows, even if the source and the destination is same. You also have to update rules dynamically to actively change flow patterns. So as network engineers, we know that there is a process by which you actually update the flow table. This method is actually saying that you do it dynamically, which we are trying to go towards. And then so Polka is the tool that the Brazilian team have invented, which uses source routing for active flow changes. And this is where we brought that in to merge with the machine learning so that we could do this active update of the rules and not be limited by the flow table sizes that exist. So before we jump into that part, just to have a precap on Hecate. So I think I've presented this before in APAN, that we read in real-time network statistics coming from this four-node topology over here as an example. So network health is given by link utilization, uh, loss being collected, and current bandwidth being occupied, and then any other traffic patterns that we can get. So we read that in as node and edge features, and then we build a graph representation of what the network is looking like. We do deep learning methods to predict per link what the future network stats are going to look like. And then based on that, we apply a greedy approach to find what is the best solution for the network to have. So for example, if it predicts that certain links are not going to be congested in the future, we might want to push those links down so that those are being used next time because we know that they are not being used. So we can actively change the network without doing some math calculations ourselves, right? So that's the approach we're going for here. So I mentioned that we're reading in NetFlow data, Persona, and SNMP data for the network health. We perform unsupervised cluster analysis and graph neural networks, and then we do the global route optimization over here. Now, one key thing which we struggled with over the last few years was this arrow. If you can see my cursor, the arrow where the routing updates are pushed down to the network was something we hadn't figured out how to do. So we were able to do the reading off of the data because working at ESNet, for example, they had a lot of APIs where you could read in real-time data that was coming in from the network. But we were trying to understand how, once you have an optimized solution, how do you actually instigate the change down into the network? So this would mean that you would actually call such as an OpenFlow API or a SDN API to actually change stuff on the network. And that was what we were trying to do. And this is where I think source routing or the Polka solution actually helped us. So this is where the Polka solution comes in, and it does this push for us. So now we can go from an end-to-end solution for AI all the way up to network change. So going into the Polka source routing, so this is work done by the Brazilian team, and they have some great papers, which I've listed over here below. It is using a source routing kind of method, and possibly the audience is obviously aware of this. It is better than traditional table-based routing because what it does is it uses a labeled flow, and that label then guides the flow as it moves through the network. So there are many protocols that exist, which either use an ordered list or other methods. So the way Polka uses is that it pops the first label, and then that label kind of guides it which particular next path it should go to. So the team has invented this idea of the Chinese remainder theorem to make sure that there are no loops in the network, and the paths that are calculated are always optimum. So there are more details of that in their papers. So they use root ID, node ID, and port ID to actually have those forwarding rules being defined in the division. This is an example of how their port ID is defined by root ID and node ID. I have an animation that describes this next. So a simple animation is that we have a source and a destination. You have a complex network in the middle where the hosts are connected to the edge switches, and then the edges are connected to the fabric of the core switches in the middle. And what they do is that in an initial setup phase, they assign each switch node IDs, and then each of the exits of those switches are assigned port labels. So that's the doors you can go out of once the label comes in. And one example over here is that they are trying to guide a path through this, a flow through this path shown horizontally from 11111 and 1011 all the way to the destination over here. And so the flow has to follow these doors. So 110, 110 as it goes through. So this animation is basically showing you how the flow goes through. The label first arrives at the first source. It pops what is written over there. It takes the one, and then it moves up all the way across the path. It gets to the edge, and then it's finally being read by the destination uh, server where it was supposed to go. So so what happens is that how we came together to merge Polka and Hecate was we redesigned our architecture to work with their architecture. So, for example, let's go into the diagram first. So initially, I showed you that Hecate was reading in real-time topology and network statistics. That is still happening. So it reads in that real-time data, but this time Polka collects this. And then Polka then queries Hecate with this data to tell me which is the best path for me to go on. So Hecate is now maintaining a database at its end, but it's updating this using what Polka is sending it. Then Hecate works out what the optimal path is, and it sends it back to Polka. And then Polka then executes the network action based on the recommendation that is coming up from Hecate. We did this because we wanted to make Hecate flexible enough to work with any kind of network device, because we're working with Polka now, and we can imagine there's going to be more network devices that might query Hecate. So we're trying to make it as flexible enough so that it can work with multiple devices. So we've restructured the whole thing to work with APIs. So now we have a Polka source routing service, Hecate AI-driven network service, and an optimizer module for route selection. And then we've added schedulers, controllers, an orchestrating plane, and data messages that are going between Polka and Hecate. So as a real-time demonstration or a proof of concept, we actually did a real network data set test by leveraging these two tools to work together. We used a dummy data set first. So this is a dummy data set of network collected over the University of Queensland, which measures Wi-Fi and LTE with different bandwidths between these different buildings. And we designed them as path 1 and LTE as path 2. So this was just to see if this works in a wireless setting, but we also showed it working on a P4 testbed afterwards. So Hecate's APIs now expose 18 machine learning algorithms that are shown in this graph above here. And depending on the data which it was receiving from the network, each of those ML algorithm was able to return that if you use me, this is the prediction accuracy I am giving you. So we can do this initially when the network is setting up, and then you can select which kind of machine learning algorithm you should use because the control is still with the user. So they can decide that, okay, this one is giving us the best approach, so we are going to use this one. So the same data set can be used for training and then testing, and then finally you can actually do it in real world as well. Default hyperparameters were used for this, and we used the mean square error as a performance metric. So these are some results from the dummy data, which I showed previously. And the most interesting part is the P4 stuff. So so we did the same thing on a P4 testbed, which is shown over here at Caltech. It was set up. And also they had another setup at SC. So we actually did this live as well. So it exposed all the paths that were between the same source and the destination. And then the data which Polka was collecting was RTT, latency, loss, link occupation. And it can collect more, but these were the 4 variables we were collecting. And then there were 3 tunnels that were set up between these. So you can see the 3 tunnels represented by the different colors over here. So those would be the paths you would go over. So when Hecate is called, it would get statistics from all these 3 tunnels, and then it will know which is the best path to go for if asked for. Because we do dynamic optimization, you can continuously adjust path selection. And you can optimize based on resource, RTT, or whichever is the optimization function you are trying to optimize on. So initially we configure a flow. So for example, this is what we showed live, was there was a flow that was configured on one path and we were getting a latency of very high, and it queried Hecate to get an optimized path. And the thing to notice here, it took very less time for the path to switch from the one path to the next to actually to continue on with the flows. So the transition time was actually very, very small, and that is the advantage Polka brings. The only latency, I guess, is just the API calls that were going on between Hecate and Polka, but the switch was very quick. And we were able to perform better experience by a reduced latency by 20 ms. In another experiment, we did flow aggregation over multiple paths. So here we were trying to optimize the bandwidth. So there were flows that were going, as you see, from 0 to 40. And then what we wanted to do was we wanted to split flows in order to actually use more optimized paths. So all the available paths that were available. So per flow, we were able to introduce different rules. And then you can see that all of those flows use different paths. So Hecate collected real-time metrics from the network, which Polka was sending. And then per flow, Hecate said, you take red, you take green, you take yellow, for example. And we were able to get better bandwidth across the network. So what's next with this? This was a very successful experiment at SC, and it helped us rethink how we are designing the AI APIs. Initially, we were trying to design a complete solution, which we've been doing or I've been doing for over a number of years. But this experiment actually showed me that if I was to redesign this as APIs and then just expose some machine learning behind to other tools to use, we could actually build very powerful systems. We just need to collaborate more with other tools. So Polka was actively switching paths and we were able to collaborate with them. We need to integrate a monitoring tool between Hecate and Polka so that they can do a better communication between the two. And we've shown a P4 implementation of this on P4 Labs. This is a GNAG effort. And we've also shown a small version of this working on Fabric. So that is something which we are continuing to work on and possibly get a paper on. And in order to do this more, we're trying to build a testbed at Oak Ridge involving NVIDIA Bluefields, Intel P4 devices, and more. And we're learning a lot about the APIs each of these devices come with, what is possible and what is not, to actually show this more as a self-driving network in the future. And that is all from me. Any questions? See if I can see you guys.
Hello. Just curious about scalability and any observations that you've had so far during your testing related to scale.
So we've tested this on a maximum of 10 nodes so far. I think from a scalability point of view, it shouldn't be. So the scalability is going to be the same challenges we have in source routing, because the paths are still being calculated between source and destination. So I think it should scale well, but we haven't tested it yet. We've only tested it in a 10-node network so far as test setups. I'll have to push that to show more of scalability results.
Any other question? I have a question. Do you think you can apply your mechanism to the overlay network?
Yes. So The way we're trying to do this is that we're making it flexible enough to work with any tool. So if we have a similar SDN kind of approach that works on an overlay network, we should be able to link the APIs with overlay networks as well.
I think if you try to deploy on the NRAN, such as the CoRAN or some other APAN networks, then I think we can deploy some the virtual load, and then we can make some overlay network. After that, we can deploy your Hecate or POICA systems. Then we can make some experiment. Then do you
Yeah,
think
sure.
do you think it is possible?
I think it is very possible. Let's work together then. So we're continuing to work on this. This experiment earned us the best paper award. So definitely, it seems like the networking community thinks that this is something we should continue working on. And yeah, let's work with the APAN folks to actually do more of a demonstration. I think that's going to be a really interesting experiment between us.
If you can make some opportunity, I will ask your help. Thank you very much.
Sure.
Is there any further question?
So I should say the code is all open source. So we're open sourcing all of this code. So if anybody's interested to go in and see, even Polka is open sourced, and this part of Hecate is also open sourced. So if you see this and you want to talk more about it, that's fine, and we'll contact you more to experiment with this.
Thank you. Thank you for presentation. Give a big hands, please. Next speaker is Dr. Yuichi Teranishi from NIST Japan.
Hi, my name is Yuichi Teranishi from NICT Japan. Thank you very much for giving us a chance to present our work. My title is Edge Computing Networking for Future AI-Driven CPS. This talk concerns to the edge computing and networking testbed and technologies we are working on for the future AI-driven CPS. So it is about networking for AI. I hope this matches this working. This is a background. In the beyond 5G era, the cyber physical system is expected to create a loop between the cyberspace and the real world. AI-driven analysis and inferences capabilities will enable the continuous loop between the real world and cyberspace. So the various data from the real world is sensed and digitized and uploaded to the cyberspace. And the data is analyzed and processed by AI, and results are used for actuations in various application services. And such a AI-driven CPS requires handling a large amount of distributed data. So in order to implement such a CPS in the existing cloud centric architecture, what we call data monopolization business model. All distributed data are transferred to the cloud companies. So the number and volume of data become enormous, but all data might not be necessary. So it causes a waste of network traffic. And the more fundamental problem is risk of the surveillance and compromising confidentiality and privacy caused by the data leakage in a centralized cloud company. And there is also issue of latency to process data in a remote cloud server. It may take more than 100 milliseconds to access the servers in the US from Japan. But many interactive applications requires a millisecond order response time. So to cope with such issue, future direction towards edge computing and networking and distributed data sharing architecture. And in this architecture, requirements include managing the user's own data, limiting who to disclose, and limiting the geographical distribution range. Such limitation is also required by the European regulations like GDPR for handling the personal information. And because computers and storage is located at the edge of the network, we can reduce the network traffic if the running process on the edge computer filters the unnecessary data to the cloud. And we can also get a response with a small latency with a short turnaround time from the edge computers. And let me discuss the other reasons why we need to use edge computing and networking. Another reason is energy efficiency. It is said that moving bits costs significantly lower than moving the power. This graph is an example of computing at the power source rather than the computing at the edge, but it takes about only 1/100 or 1/600 cost in moving bits than power transfer for AI processing. That means processing data near power source is more cost effective. And particularly when the user is located close to the renewable energy sources, such as solar energy and wind energy and so on. And the other reason is trends in the cost of the computing and communication. Generally, the processing reduces the size of the data, and the computing cost is reduced drastically faster than the communication cost in recent years. It is less than 1/100 in cost reduction ratio in 20 years. So it would be reasonable to migrate the process to the edge computer located closer to the data than sending the large amount of data to the clouds. And there is also an issue of the efficiency to provide a high communication bandwidth. As you know, the throughput of TCP/IP depends on the round trip time, and the longer the RTT, the smaller the bandwidth. So the situation is the same in the recently proposed QUIC protocol. This right side figure shows the latency in QUIC changing the distance. The throughput becomes half when the round trip time is 10 times longer. And we NICT have been providing the beyond 5G IoT testbed services. Simply, I call it here B5G testbed. including the edge computing and networking for future AI-driven CPS. The testbed aims to accelerate the research, development, and social implementation of beyond 5G technologies through the collaboration among these diverse stakeholders. This testbed offers three layers of network services. From the bottom layer, there is a network layer, B5G virtualization infrastructure, and B5G mobile environment. And there is also a middleware layer, we call it serial demonstration environment. And on top of these layers, there is a platform layer, which we call data-centric cloud services, DCCS. And this network layer and middleware layer testbeds provides features to support edge computing and networking, and the platform layer, DCCS, corresponds to the AI in the cloud. And let me look at the edge computing and networking support functions of our testbed. And we provide a network layer testbed called B5G Reliable Virtualization Infrastructure, which provides virtual machines or NFBs on the several sites in Japan. And it also provides a virtualized network among these virtual machines for each user. The network layer testbed also includes a B5G mobile environment, which consists of three environments. The one is a mobile application development environment, which employs a hardware-based base stations network, assuming the enhancement towards the B5G. So which enables evaluations of the application technologies related to the 5G network. The other one is a mobile network development environment, which is a cloud-native base station equipment using the general purpose services and antennas. So the third one is a base station development environment. This is for the research and development for the mobile system using the multiple base stations. So such B5G mobile environment is closely connected to the virtual infrastructure presented in the previous slide. And in our middleware layer, we offer the testbed called serial environment. It allows users to verify the entire system behaviors through the combination of the simulations, emulations, and real networking devices. And in the following, I would like to introduce some researches related to the edge computing and networking on the testbed for AI-driven CPS applications. The first one is a research on IoT edge computing architecture, which is a rather old research, but we proposed a two-layered architecture, ECP PaaS and ECEAS, which corresponds to the platform as a service and infrastructure as a service for edge computing. The EC PaaS manages processes for the IoT applications, and ECEAS manages a virtual environment with a restriction of latency. And ECEAS layer, ECEAS corresponds to the network layer with and the middleware layer in the testbed. And this ECER's technology, as this technology, we proposed a power-saving management technique, which is essential for the sustainable AI deployment at the edge. And in this proposed method, resources are aggregated as long as the requirement of the response time is satisfied. The time-critical applications are located at the edge device, but for the applications that do not require a small response time, such as batch processes or normal web application, the resources allocated by aggregating the multiple applications at once, and the power consumption is reduced when unnecessary services are turned off. And as a EC path layer, we proposed a dynamic data flow processing platform. We used such directed graph to present data flow in the stream data processing. And this graph shows an example of data flow. And to run such data flow process, all processes can be executed if there are enough network and computing resources on the cloud. But for efficiency, to achieve the required response time, the process might be required to be replicated and executed on the edge and cloud as a distributed services. And if the number of data source is increased, the number of the replicate process may need to be increased. So we call such dynamic allocation as a dynamic data flow processing. And this video shows a sample AI processing scenario. And upper left is the original video. And if the normal edge computing environment, the process does not run correctly because of the heavy computation load. But our proposed system runs processes on 2 edge servers, so we can obtain the smooth result. But if the process runs on the cloud with two cloud servers, the result is delayed. As you can see, the cars from the other side is delayed in this result. So that's the edge computing example. And another one is data sharing architecture for edge computing and networking. In our research group, we have been studying on the data management in the edge network. It is called NICT secure off-chain storage. Its main features are off-chain storage for the blockchain network. And there are 2 key components, secure in-network storage, UCNC, and decentralized storage, which we call IPFS with NICT extension. These features runs in the B5G testbed for application including the AI training for the maintaining data securely across the distributed data edge nodes. And the first key component is a UCNC, our secure in-network storage function. UCNC is user-centric in-network caching, which has an in-network storage function with a secure and efficient access to the data managed on the blockchain. Network layer functions enables the limitation of the distribution range, and this mechanism is developed based on the NICD's open source called C4, and it enables low latency access with in-network cache and reduced load in the data sources and the network. And it also enables the fine-grained access control by ciphertext policy attribute-based encryptions, CPABE. And the key feature of the UCNC is limiting the distribution range in the network layer, which is a mechanism by detecting the data is successfully decrypted or not, which we believe is one of the important feature for data management for the secure processing. And another key component is IPFS with extension. IPFS is an acronym of Interplanetary File System, which is commonly used as off-chain storage in the blockchain services. And we implemented a routing layer that is tolerant to eclipse attack, one of the drawbacks in the IPFS original routing layer. And our plugin implementation allows applications to use the standard APIs. So there's no need to worry about changes in the routing layer from the applications. And we have found that even when the 30% of nodes are occupied by the adversary, it maintains a 99.7% success ratio. And we've also confirmed that it can reduce the maximum traffic per IPFS node by around 80%. So such mechanism separates the data management from AI processing. So we believe such secure data management in the distributed network is crucial in the future secure AI, including LLM. And fortunately, our paper has been accepted in the next Infocom, so you can see the detail when the paper is published. So that's all from me. Thank you very much.
Any question?
Hello. Yes, I have a question. Well, your presentation was very good. It was very well explained. Actually, I have a question regarding the proposed model that you just proposed, and actually, I have it. How can we differentiate between the normal applications and the time-critical applications for this particular proposed model? Like, did you experience any priority for critical task on edge computing in relation to response time? Because for critical task, we need the low response time in this case. So did you see anything for the critical tasks on edge?
You mean?
Yeah, how can we differentiate the normal applications and time critical applications in this case?
You mean how do we distinguish?
Yeah, distinguish
the time critical or not?
Yes.
In our experiment, we only labeled each application,
Okay.
but it may be, yes, I think the application should specify their requirement.
Yes, the
Yeah.
priority. I mean, the
Yeah.
time critical applications.
Yes, yes.
Yeah, the task should be prioritized, like whether it requires the low response time or the high response time. The tasks should be prioritized like this. So that's
Yes.
what I'm asking. Yeah. Yeah. So that was my
So
question.
we just
Okay.
yeah,
Okay.
labeled.
Okay.
Yeah,
Thank you. Thank you so much.
Okay. Thank you for your presentation. We can go to the next presentation.
Thank you very much.
Thank you. Give him big hands, please. Next speaker is Ki-hyun Kim from KIST, Korea.
Uh, uh, Hello everyone. My name is Ki-hyun Kim. I work at KIST from Korea. I'm in charge of development platform in CreoNet AI research platform. This presentation is about a platform that provides an AI research environment for AI researcher. So it is a platform that provides an environment where researchers can easily use the computing environment and freely share researcher results among users using this platform. Let me start by explaining the background. The global research trend has changed since 10 years ago. Big data is overflowing with the advent of super facilities that produce large amounts of data from research equipment. It will change from the existing simulation-oriented research environment to a research environment for processing and calculating data. Although these types of research have changed, the technology of the network has not been able to support these research changes. Accordingly, the global trend has changed to big data superhighway using Science DMG. The Science DMG developed a new concept at ESNet in the United States. Science DMG is a concept encompassing specialized network design, system optimization, and transmission node development, and software optimization technologies for transmitting, sharing, and storing the big data in the data-intensive science field. Various studies have been developed and derived based on Science DMG, and it has become the starting point of our various research platforms. And then, after transmitting data, it has changed to our research environment where data processing and computing are performed during idle time. This is our platform introduction. Our platform is based on PRP Nautilus system in USA. CreoNet AI research platform is infrastructure for research and educational institutions to carry out scientific research in various fields. through this platform, convergence of national science and technology can be achieved. This platform consists of two components. Components are data network system and AI platform automation system. Data network system consists the network infrastructure that safe on security aspect and transmit big data without packing loss using data transfer load. AI platform automation system is a system that automate container-based AI programming and GPU, CPU computing processes. The purpose of the research platform provides an efficient platform to share computing resources by converging the AI researches of institute. And this enables convergence of diverse field of AI algorithm utilization in scientific application. I will explain the AI platform automation system in detail. Most of the created AI research platform was built using open source. Open source platform were installed for platform management, and the web interface was developed so that users can use them more easily. As open source is used to manage the platform, Kubernetes, which creates and manages the most important containers of the platform. And the self-storage are used for storage, and the Harbor is used as a private image registry. System monitoring uses Prometheus and Grafana, and the server logs and errors use Elasticsearch and Kibana. Open source is used by users to perform AI tasks or programming using R, MPI, PyTorch, TensorFlow, Python, and so on. For our images, we recreate AI environment for this platform. It also provides a command line interface and web interface. The structure of the current AI research environment provision platform is as follows. The most important role among each component is the Kubernetes module. And through this module, all functions are developed to operate on a container basis. And the web interface is implemented to automate a series of processes such as creation, deletion, and update of PVC service ingress pod operating in Kubernetes. From the user's point of the view in the structure, it costs of login, computing, transfer, story, and monitoring. I will explain in more detail about the computing and storage monitoring part. The Kubeflow module is implemented for distributed computing. First, let's talk about the computing module. The computing module is divided into two parts, individual computing environment and distributed computing environment. Now, I will explain individual computing environment. There are various images on our platform, but I will explain just using Jupyter Notebook as an example. Most users this platform utilize Jupyter Notebook. Individual users are allocated the computing resources they want to create a container. Jupyter Notebook is an open source web application that allows you to create and share documents including live code, equations, visualization, and so on, and is mainly used for data processing, modeling, and machine learning. Specifically, it is a web-based tool that allows you to intercollectively operate and visual data in real time. When users create a container, a web URI is automatically created, and if they enter through the URL, they enter the Jupyter Notebook UI as shown in the figure below. The AI coding interface that can be used inside provide various interfaces such as Python, TensorFlow, PyTorch, Keras, and MPI, and so on. Next, in order to perform the computing module, we need a system for storing images. Harbor is a tool for private image registry. In our system, it is used to provide images in private and public environments. In the case of a private image, users store the images they create in Harbor, and the provided system provides an environment where users can share them according to the user's permission. However, since Docker Hub has a limited number of private images to store, so we use Harbor. Harbor is not limit, and our images currently released are provided to all users through a web interface after the administrator has verified the security. Next, the storage module. Storage module consists of SAP. SAP Storage is an open source software-defined storage platform that makes it easy to manage storage servers with software. It provides object storage, block storage, and file system interfaces, and look to be used together, act as an orchestrator to linkage, Kubernetes, and SAP storage. When configuring the storage, it is configured as object storage. Object storage enables data transfer with other users, and when object storage is configured, it is currently configured to link with other cloud platform to transfer the data I used to the cloud platform. In addition, in the case of object storage, you can configure a dedicated data transmission environment with other servers that you use by using the S3 protocol. Next is the monitoring module. The monitoring module used Prometheus and Grafana. By using the Kubernetes resource monitoring API, the resource information of all DTN servers is sent to Prometheus to collect index values. Using the collected value, Grafana composes the web UI and displays it in graph form. This is the graph configured in the currently configured monitoring system. The Creator AI research platform developed a web interface by automating the following processes. The main function are login, storage creation, and container creation. In fact, the container creation part is the most automated part, and this allows users to easily configure a computing environment In addition, the web interface use Nginx to connect to domains, and a token value is configured when each user creates a computing environment, and this is applied to web security. We developed it and applied this automation to a web interface. The fields that are utilizing this platform are NLP environment and agriculture field. In addition, a project was carried out to develop a big data management platform for the agriculture field based on this platform. Now, I will show you a demo of the platform we developed. This demo focuses on the process of creating container and creating storage. Yeah, the user login, and then if you access the portal, you can check the resource, resource usage, and where the server is installed. Yeah, and then next we will proceed with creating a container. To create a container, enter a name, select an image, select resources. Yeah. Resources, select storage, and then click the create button. Let's access the Jupyter Notebook, which is the created container. You can perform AI computing through this. It provides a command line interface and a web interface. So now access the web interface. And you can also check the monitoring of the container. Yeah. So pod resources check. After that, we will access the storage creation. Create the storage by selecting the storage name and the size, and then create. Yeah, so and then create the create the storage. It provides a monitoring environment that calculates the resource usage of the Kubernetes node in number. Yeah. And the demo on the next page. Second computing model is distributed computing. Distributed computing is used Kubeflow. Kubeflow is open source machine learning platform designed to enable using machine learning pipelines to orchestrate compliant workflow learning on Kubernetes. Kubeflow provides various frameworks for constructing researchers' machine learning models. The purpose of Kubeflow in this platform is for distributed computing. Distributed computing, distributed training in Kubeflow provides a distributed computing environment. We provide distributed computing for users who want to process AI training quickly. To use distributed computing, the user needs distributed computing programming skill. Therefore, for distributed computing programming technology, we provide various examples so that user can easily use examples that fit their research environment. Thank you for listening to my presentation. Any have a question?
I have a simple question.
Yeah.
How many users is using your environment?
How many GPU or CPU resources?
No. How many users?
Users. Actually, now 10 or yeah, some people, yeah. So we will yeah, some service provided for our CREONet researchers.
Okay.
Yeah.
Thank you. Thank you very much.
Thank you. Time is very short, so we can go to the next speaker. Give me, I'm sorry, big hands. Next speaker is Dr. Chang Hua Pei from CNIC China. Dr. Chang Hua Pei, are you there?
Yeah, I can hear. I can hear.
Please start
Can
your
you?
presentation.
Okay, let me share my screen. Okay, can you see my slides?
Yes.
Okay. Hello, everyone. I'm Chang Hua Pei from Computer Network Information Center, Chinese Academy of Sciences. And I'm very glad to be invited to give a talk about the AI-driven network. And my topic is about beyond sharing, conflict with multivariate time series anomaly detection. And this is a joint work conducted by Computer Network Information Center and Kuaishou Technology and Tsinghua University. First, I would like to introduce the background of this work. Currently, no matter network systems or internet services such as routers or the switches, and there are monitor systems. And the current monitor systems in internet services provides insights by collecting metrics like response time, CPU usage, and queries per second. And we call a set of time series. And this kind of data are stored in the form of time series. And we call a set of time series as multivariate time series. But the upcoming multivariate time series may deviate from normal patterns, either one curve against its historical patterns, as shown in this slide, or it doesn't align with the joint distribution of multivariate time series. And you can see from the left side, and there are three matrices, and the green ones is different from the red ones, and they does not align with the joint distributions at that time step. So the multivariate anomaly detection is the task to judge if there are deviations according to the matrix. By detecting anomalies earlier on, proper actions can be taken to mitigate risks or ensure the smooth operation of the internet services. So the most important thing is to learning the reasonable joint distribution because you can see from these two matrices, the normal patterns, we can see that they show the positive correlation as the queries per second increase and the CPU usage should increase. But in the abnormal case, as the queries per second increase, the CPU may decrease. So this indicates anomaly. The main goal of our research is to reasonably to learn the intermatrix dependencies. This kind of deviation usually means the abnormal pattern, such as, for example, the code bugs or the hardware failures. However, there are some existing methods to modeling the multivariate time series and to detect anomalies, but this method seems not robust enough by modeling intermatrix dependencies. Let me give an example. We can see that there are 6 matrices, and it's obvious the first 3 ones show the same pattern, and the bottom 3 ones another pattern. And we can what we expected is to learn the intermatrix dependencies between the M0, M1, and M2. But we do not want the model to learn the dependencies between the M0 and M3. And we call this kind of negative correlation as the conflict. But in current models, they cannot isolate this kind of conflict very well. We here show an example about work called TransAD from the WellDB 2022. And we can see the red curve is the raw data of the M3, and the green curve is the reconstructed curves by the model. And the anomaly detection is to compare between the reconstructed time series and the original time series. If the gap exceeds a certain threshold, we may indicate that there is an anomaly happen. So what we expected is to well reconstructed the M3 matrix, but affected by the M1 and the M2. We can see that the reconstructed time series, which is the green one, is not that good because it's greatly affected by the value of the M0 or M1. So we want to propose a method to address this kind of conflict, and we finally choose a method called the MMOE, which is well known by currently because such as DeepSeek large language models also use such kind of MOE structures. But there's another M before MOE. This M indicates the multiple gates. So the MMOE framework proposed by Google is designed to automatically capture either shared tasks, informations, or task-specific information, which is naturally fit for solving our conflicts. So in this framework, we can see that from the structure, in the right side, there are multiple exports. Each export extracts information from the raw input, and there are gates whose parameters, depending on the input, will determine how much each export contributes to the final output. So why can MMOE address the conflict between the multiple time matrix? We can see that on the one hand, each gate will combine the embeddings from the export models independently, which can effectively avoid the introduction all of the irrelevant features. On the other hand, independent learning stage, known as a tower, which is shown at the upper side of the picture. We can see that the isolate tire is designed for each matrix to partially isolate the impact of gradient disorder caused by the conflict. However, as Vanilla MMOE is designed for multitask learning, it works not very well in multivariate time series anomaly detection. And we observe that MMOE faces three challenges when in anomaly detection. The first one is that the expert in vanilla MMOE consists of only feed-forward network, and it's unable to capture both the temporal and intermetric dependencies at the same time. So it's not designed the simple feed-forward or MLP is not designed for the time series data. So in our method, we replace the expert network with the multi-scale convolutional network to capture the both spatial, temporal, and the intermetric dependencies. The second challenge is that MMOE uses the whole input to generate the weight given by the gate, which is shown by the red circle in the picture. But we can see that in our previous experiment, if we use the whole time series set, the performance degrade very greatly. This is mainly because that the gate is used for selecting the right expert, but which expert should contribute more should decided by the matrix itself. So a matrix should pay more attention to its historical information instead of other matrix. So we use, instead of using all time series to generate weights for the gate network, we only use the relevant and independent time series of itself to select the expert. So we generate embedding combinations solely based on the current matrix history instead of all the time series, and this greatly improves the accuracy by capturing more specific dependencies for each matrix. The third one is the converge issues, and we can see that if M1 and MK is similar, but the corresponding weight generated by the gate is not that similar because they are separate expert and separate gates. So in this case, the expert have to learn two expressions of the same pattern, and the learning process of the expert would be confused and chaotic, and this will cause the convergence problems. To address this problem, we introduce a shared gate that allows the similar curves to generate similar weights. The weight refers to the output of the gate network, and enhancing the embedding convergence on important features and improving the detecting performance. So using all these kind of designs, we have powerful network, which can effectively detect anomalies of multivariant time series, which come from routers such as switches or the host load in the cloud computing network. So in the left part, I will introduce the evaluation result and answer the following questions. The first research questions is we want to check, can our proposed KAD method effectively handle the conflicts? Then we want to answer, do the well-designed structure works as it's expected? And the last one, we want to find whether can different experts know the representations of data from different perspectives. So we can say the CAD effectively handles the conflict let's return to the example of the conflict example mentioned earlier. Compared with the SOTA method, our method can idly isolate the conflict in time series, which we can see from the 1, 2, 3, 4, the fourth curve of the red curve, we can see we are not affected by the irrelevant time series. We can construct the time series very well. And we also conducted experiment on well-known MIT series along time anomaly detection dataset and employ the point adjustment. And we can see that our method outperforms the currently SOTA method, and we solve the conflict issues and greatly improve the performance. Also, we conduct the ablation studies. We can see from this table, we remove different part of our model, such as convolutional layer and feature selection and gate network and shared gate and personalized gate. And we can see that the experiment confirms each of our component greatly contributes to the overall performance. And in the last ablation study, we give visualization. A key observation from the picture is that we can see that by visualizing the hidden embeddings of different experts, there are 5 experts from 0 to 4 in the left picture, and we can see that by visualizing the embedding and each expert well separated in the hidden vector space proves that expert ability to disconcert the abundant but distinct features. So this is the last page of my slides, and in conclusion, we found that conflict arises when the features among different curves are inconsistent, which lead to poor performance if collections are mistakenly or falsely established in the SOTA method. So after we propose the CAD method, we effectively address these conflict issues through the utilization of the MMOE framework and the we use task-oriented, we use a comp of optimization designs such as task-oriented feature selection and the incorporation of the personalized and shared gate. So that's all for my talk. And is there any questions?
Thank you for presentation. Question?
Yes, thank you very much. My name is Professor Shiroto from Gakushin University. In the last picture of your result by CAD, the two-dimensional dimensionally deduction the TSNE. So, if possible, I would like to know the meaning of the principal component and the second one. So, my second question is, I wonder if you can make Gen AI interpret it or not.
So
Principal component meaning.
Different component meaning in this picture, right?
The two-dimensional
Okay, I know. I understand your question.
Reducing you did by using TSNE.
Yes,
so I would like to the meaning of each axis.
each x-axis and y-axis, right? There's no very explicit meanings of each axis, such as x-axis and y-axis. The design goal of the TSNE is to visualize the high-dimensional data into a 2D dimensional. So the only meaning can reflect from this picture is that you can only see the clustering factor in this picture, such as you can only see whether
I
they are
understand
separate.
what you're saying. So the very complicated result. So instead of human beings, can we make Gen AI interpret it or report the essence of the difference also? Gen AI instead of human being interpretation.
What do you mean by GNI?
As future research, I would like to make Gen AI interpret the each the axis meaning, interpret the each axis meaning to when we handle the time series data. So.
Okay. So it's a pity that there's no exact meaning of this axis. So this is only a visualization to say whether they are separate or not, to see whether the hidden vectors. So you can see that you can imagine that if you have a vector, if you have 5 or 6 dimensions, so it seems like you can visualize the embeddings in a 6-dimensional space. So each axis in this 6-dimensional to have meaning of the corresponding dimension of this vector, but it cannot be visualized very well, and you cannot plot on this slide. So the method of TSNE is to reduce the maybe 6-dimensional into the 2-dimensional. So you can it uses a projection from the 6-dimensional to 2-dimensional. You can imagine this graph is a visualization of 2-dimensional vector, but it uses a complicated projection. So if you can understand this figure, the meaning of the x-axis is 1-dimensional of the embedding, and the y-axis is another axis of the embedding. But in the theoretical meanings, it's not very that simple. I mean.
Thank you for the specialized question and answer. Thank you. Thank you for the presentation. Give him big hands, please.
Thank you very much.
Now our session ends. Then our slide files are available in the website. Then you can check the slide files. Our second session will start 11 a.m. Thank you for coming. Then I hope you can come to again to the second session. Thank you.